Walter Belgers en zijn talk over de Gigatron. Dus applaus voor Walter.
Well, good evening. Thanks for showing up at this late hour, and thanks for having me here. It's nice to be at Hacker Hotel. It's my first time at Hacker Hotel. I like the logo with the PCB drawings. So actually Marcel couldn't make it. My name is Walter Belgers, and this is the story of how we built the Gigatron computer and how it works. So this is the actual system. So this all started just over a year ago when Marcel actually started the project, and he bought a bag of microchips. Why does this not work? Microchips, no. Microchips, a scope, and a soldering iron. And these microchips are actually quite old. I mean, these series were built in the 70s, used in the 70s, 80s. You can still buy them. And they're fairly simple. So they contain simple AND gates, NOR gates, shift registers, counters, stuff like that. But what can you build using those components? Well, in the 70s, they were already around. And in that time, you had Steve Wozniak, or the Woz. And he was at the time working at HP. And his friend Steve Jobs was working at Atari. And Atari was building Asteroids, a new console game, arcade game. And typically, those arcade games would contain up to 190 of those TTL chips. And Steve Jobs got the job to reduce this as much as he could. And he actually gave the job to Steve Wozniak, who built the game Breakout, is it? Yeah, in 44 chips in the end. So it was really a low amount. And Atari then brought it to the market. In fact, they bumped it up to 100 chips to make it really stable and reliable. But it was quite a feat. It looks like it's a color game, but in fact it's black and white with a color overlay on top. And this is the actual original board of that game. So that's what you can do with a bunch of TTL chips. Build a computer game. Of course, Steve Wozniak and Steve Jobs then went on and they built the Apple computer. And so this is also with TTL logic, but what's special is that over here we see a MOS 6502 microprocessor. And the Apple One computer has this microprocessor running at 1 megahertz, 4K ROM and RAM, monochrome output. And but this is using a microprocessor, and a microprocessor is actually quite complex on the inside. We were looking at our grab bag. Actually, I had some old microchips lying in my own attic, and you can see the date code. So this is from week 19 of 1976, so those are quite old. In fact, at that time, we were looking like this. And, well, what can we build that is modern and uses those chips? And over the course of a few weeks or even months, Marcel built this on his breadboard, an actual working computer that is now looking like this. It's an actual working computer without the microprocessor. So there's no 6502 or any other microprocessor. The microprocessor, the central processing unit, is on this board. Actually, most of what you see here is the central processing unit. And in my talk, I will now explain how all of these components work, what the system can do, and also all the design decisions we had to make during the development of the Gigatron computer. And this will then also teach you how a typical microcomputer works. By the way, if you have any questions, just shout them out. So let's look at a typical computer. Normally you have internal memory, you have external memory like disks, floppy disks, etc. You have some kind of input, keyboard, output, screen. And there's the central processing unit or CPU. And the CPU can be subdivided in internal CPU accessible memory, an algorithmic unit that can do calculations, and the control unit is actually controlling what is happening within the CPU. And we just did away with disks and complicated external memory right away. There's no disks attached. Now, for the internal memory, we have used an EEPROM, so that's an erasable programmable memory, and a RAM chip. So we have RAM and ROM. And we needed input, so we thought about having a few buttons, and we needed output, so we were thinking of a LED matrix to do some tic-tac-toe kind of game. So that was the first goal of the system. Now we have a ROM that can store non-volatile stuff, and we have a RAM chip. And now there's this problem of how to communicate between the ROM and the RAM chip. And actually there are several ways of doing this. And the most well-known way is making a von Neumann architecture. And in this architecture, this is just one memory. There is one memory that can be shared with program data and actual data. So the program is in the same memory as the data. Actually, in the beginning of computers, this was not the normal way of doing this. This was invented by a group of people building the EDSEC computer, the EDVEC computer, and von Neumann happened to be in that team, and his name got on the paper describing this architecture. Before that, the first computers had the Harvard architecture, and in this architecture, you have a separate memory containing the actual program, and a separate memory in which you can store and read data. Now this is a little bit more easy hardware-wise, but it's more difficult to use. So we had the first choice, the first of many choices. I will talk about a few more choices later on. What do we do? Von Neumann or Harvard? And we decided that we are going to keep the hardware as simple as we can. And especially if we can solve the problems that will give us later on in software. So I was talking to somebody else after one of my presentations, and there was a guy saying, well, this is what we hear all the time as hardware developers. Everybody says, well, we'll fix it in software later, and then all the software guys have to fix all the stuff. But we were doing both the software and the hardware, so it was our problem anyway. So we decide simple hardware, so that means a Harvard architecture. So here's the same schematic, but a little bit differently drawn, with the control unit as the main component controlling the ALU, input, output, and memory. So as I said, we chose for separate program and data memory. So the EEPROM holds the program, and we have a separate RAM in which you can read and write data. Now let's take a look at the program memory. So that's the EEPROM that holds the instructions that tell the computer what to do. So this is where the control unit comes into place. The control unit will be doing the stuff that's written in the instructions. The instructions come out of the EEPROM one by one because we have a program counter that counts the address of which the EEPROM at which the EEPROM is addressed. And this you can see on the board. So I have slides with the whole board, and I can highlight that these 4 chips are the program counter, 4 bit each, and we have a clock circuit to generate a pulse, and we have the EEPROM holding the program data. And of course, to get this running, we need power, so we have a few components added to provide a stable power and some protection against shortcut and stuff like that. So the EEPROM holds the operands, the instructions. So we have the program counter pointing at an address in the EEPROM, and out comes an instruction. Now we have the second design decision. What does an instruction do? And here we have 2 paths we can follow. We can build a RISC architecture, or we can build a CISC architecture. In RISC, it's really easy. One instruction does one thing. In CISC, one instruction can do multiple things. So the CPU, the processing unit, has some kind of internal program, microcode, that converts this into smaller steps that are executed in sequence. So that's fairly complex. And if you look at the 6502 processor that was in the Apple I, there could be up to 7 micro instructions per clock cycle. So you need a lot of hardware to do that. And you can also see that if you, and I have to look at this, this is the Z80 processor. So this is the die of the actual processor. You see the algorithmic unit is quite small when you compare it to the instruction decoder that needs to make sure that everything happens as it should happen. So it's quite complicated. Here you see the opcodes for a PIC processor, and you see this is RISC. All the opcodes are the same length. Each opcode does one thing. If you look at Z80 programming language or the opcodes, they can also be 1, 2, 3, or even more bytes long. So that's really complicated. So we make it simple. We use RISC. So this means the program gets a little bit longer because the instructions by themselves cannot do a whole lot of stuff. Now we also need operands. So if we have an instruction that puts some data in RAM, we also need to tell it what data it needs to put in RAM. And that's in the operand. In the original design, we had a ROM containing the instructions and a separate ROM containing the operands. And what we decided is that every instruction has one operand. Even if the instruction doesn't need an operand, for each instruction we also read out an operand from the second EEPROM. And in the eventual design we thought, well, we can just combine this into an EEPROM that has 16-bit output. So that's what's in the actual board. So the two EEPROMs are combined in one. So out comes 16 bits, and the first 8 are the instruction, always 8-bit, and the second 8 are always one operand. So each instruction is one 8-bit instruction. It has one set of 8 bits of data, if you use it or not. There's no microcode, so each instruction is just one clock cycle and does one thing. So that's fairly simple. What we also have, and that's interesting, is that if an instruction is working on the opcode, if an instruction is being executed, does something, then at the same time we can already fetch the next instruction. And then you get what's called pipelining. We get the data from the EEPROM, but we already had some old data there that's now being executed. And then this is being executed, a new one is fetched, and this goes in parallel. And we can pipeline. And therefore, we need registers to temporarily hold the 8 bits of instruction, 8 bits of data, the other way around. So those are there. And because of this pipelining, something really weird happens. When you do a branch instruction, so the branch instruction, you jump to another piece of code. Now the problem is that if you execute the branch, the instruction just after the branch was already fetched. So if you branch to somewhere else, then first that pending instruction will be executed, even if you're jumping somewhere else. So you have to take this into account. So you can do it in several ways. One way of doing this is that whenever you do a branch instruction, you put a knob just after it. So you can do this in the hardware itself. So for instance, Spark processors do this. They have pipelining, but you don't have to care about this because internally they put in a knob. Or you can leave it there, and for instance, the ARM processor does that. So you need to take this into account. You can also use it to make your code shorter and more unintelligible. For instance, this loop will load the accumulator with 0. Here it will branch to 0. But if it branches, the next instruction has already been fetched and will be executed. So we can jump to one instruction further and skip this instruction, but put the instruction after the branch, because we know that it will be executed. So that's kind of a ugly way of making this, doing this. But as we said, we keep the hardware simple and we fix this in software. So if we have, for instance, a compiler that will compile our machine instructions, we can put all the intelligence about this in the compiler and we don't have to worry about it. Going back, the EEPROM. 8 bits instruction, 8 bits operand every time. And so the instructions determine what's happening in the system. So there's this orchestrator that determines who has access to the bus, what the program counter does, what the ALU does. And now it's up to us as designers of this computer to determine what these bits mean. It's up to us as the designers to get some kind of mapping here. And this is what we came up with. We said the first 2 bits, we decide that they determine who has access to the bus on the system. The next 3 bits will be either the address mode or a branch condition. And I will go into more detail. And the last three are the actual instruction, what the computer is computing. Now the bus access. We have 2 bits, so 4 values, and this tells who accesses the bus. So it's either the operand is put on the bus, so this is directly from the EEPROM onto the bus. We can put a RAM value on the bus, we can put the accumulator value on the bus, and we can put the input to the bus. So we have an input bus, buffers here to store the data and to put it on the bus. We also have registers. We have the program counter. So the program counter can only be set using a jump instruction, a branch instruction, and it automatically increments with 1 during running. We have an instruction register and a D register. So those are just buffers between the EEPROM and the bus. We have 1 accumulator that contains the result of the arithmetic operation within the ALU. And we have an X and Y register. They can be used to point at an address in the RAM. And what's interesting is, first of all, one is a buffer and the other is a counter. I will explain why that is later. And also they are write only. So we can put something in those registers, but we cannot read them out again. And that is also to keep the hardware simple. If we were to be able to read it, we need to have extra hardware. And because we write the data ourselves, we know what's in it anyway. So why should you be able to read what's in there? And we have some registers for output and input that I will explain later as well. Note, we have no things such as stack pointers. So here are the registers: accumulator, register, X register, and Y. And because X is a counter, it needs 2 chips, and Y is a buffer. Okay, back to the instructions. So I explained the first 2 bits. They are they tell who has access to the bus. And then the last 3 bits are the actual instruction. What does the ALU do? Because we have there are 8 possibilities, and the first 6 are arithmetic. So on the board we have an ALU, an algorithmic logic unit, that can do algorithmic stuff. It takes 2 inputs, the accumulator, register, and the bus. It does something, and out comes a result. You have to tell it what to do, and there's also something else coming out, status. So this is normally status register saying it's 0, or it's non-zero, it's parity, it has a carry. Well, we only have a carry flag. That's the only thing that comes out. Does the operation give you a carry or not? And if you have one of these instructions, then those 3 bits mean that's an addressing mode. So if you use the other instruction, this will indicate a branch mode, but if you do an arithmetic operation, those 3 bits are the address mode. And that actually consists of 2 things. It tells you which RAM address is used, and it tells you where the ALU goes to. So let me make it clear with an example. So if the instruction was this instruction, then we see that the first 2 bits are 0, 1, which means the RAM value goes to the bus. So the output of the RAM chip goes to the bus. Because we have here this address mode, that means that the RAM address is set to the contents of the Y register and what's in the data in the operand. So the value of where we read in the RAM comes from the Y register and the operand. We also have here AC, which means that the result of the computation goes to the accumulator. And the last 3 bits tell you what the instruction is, add. So the ALU is doing an add instruction. Okay, so and we can make, of course, all of the combinations that we would like to do all of these arithmetic operations on all kinds of input and store it in all kinds of places. Yeah, so the part on the board that determines what is happening, so that's the instruction decoder and the address mode decoder, is actually a bunch of diodes. So it's kind of like a sort of built-in ROM lookup table using diodes to orchestrate this bit is on, so that part of the hardware needs to do something. Which is also nice, you can actually see the instruction decoder in here, and if you like, you could say, well, I don't like this instruction, I'd like to rewire the board to do something else. Just put the diode in another place, and you change the instruction set of the computer. So that's the first of the 6 instructions. There are 2 more. One is called store, and that's the only instruction that we have to put something into RAM. Let's go back. Store puts what's on the bus into RAM, and again, if you look at the address mode, this determines at what address we are writing in the RAM. So store is the instruction to put something in the RAM. And the last one is the branch instruction. And when you use the branch instruction, then the middle 3 bits no longer indicate an address mode, but the branch condition. When do we execute this branch? There are 3 bits, so there are 8 possibilities. And these are the possibilities that we have built in. Let's look at those in more detail. So you need to build this in hardware somehow. So we need to check if the accumulator is larger than 0, smaller, etc., etc. But we don't have all these flags coming out of the ALU. So how do we determine if this is true or not? Well, we can make this truth table. So if we can check if the accumulator is 0, smaller than 0, or larger than 0, then by using a combination of these 3, we can make all those 8 combinations. So for always, it's fine if this is true, or this is true, or this is true. And if you want to be sure that the accumulator is 0, it must be 0 and not smaller than or bigger than 0. Okay, so now the trick is, how do we get to know if this is true or not? Well, the simplest is AC is smaller than 0. Because we work in the 2's complement, if the most significant bit of the accumulator is 1, then we know that this is a negative number. So that's simple, just 1 bit we need to check to see if the accumulator is smaller than 0. But the other 2, now here comes a nice trick. If the accumulator is 0, we check. What we do is we let the accumulator, we let the ALU compute minus AC. So the accumulator, the ALU is making a computation, it negates the accumulator, and then we get a carry if and only if the accumulator was 0. Because if you make a positive number negative, that's no problem, and vice versa. But if you make 0 negated, you get a 1, all ones with a carry. So this is also quite simple to check. Then all that's left is AC is bigger than 0. We cannot just check if the most significant bit is 0, because that's also 0 for AC is 0. Well, sorry, this was very cool to do. This we can rewrite as the accumulator must be 0 or larger, and it must not be 0, which we can easily compute from these 2 values. So we have very simple input, and just with a few NAND OR gates, we can make this whole truth table. So if we look at the instructions, for the first 6, we have the ALU calculate something that we need to calculate. For the branch, we also need to the ALU to calculate something, minus AC, to get that carry bit. And if we do a store, then the ALU is not doing anything, and well, let's just let it compute the accumulator, or let it output pass through the accumulator. So if we do a store instruction, at the same time the accumulator can be copied using the addressing mode to a register. So we can do 2 things at the same time. We can store something in RAM, and at the same time the accumulator is being stored in some kind of register. Now the ALU that does all the computation could be implemented using dedicated chips. So these are 4-bit ALU chips, and they're really big. They contain maybe 75 logic gates, and we decided not to do this. They don't look right on the board. They're way too big. They are hard to get. And we found an article by a German guy who built a really neat accumulator out of 10 regular chips. And it will be a talk of an hour in itself to explain how that all works.
Almost there.
Righty, thanks. So this is all we need, those 10 chips to implement a full 8-bit ALU. So that's nice. Now the address mode, to recap, we have these possibilities. So we can use 0 and then the operand. So that's kind of a 0-page direct addressing mode. We can use 0 and then the X register, which is like a 0-page indirect address mode. And we have 2 modes with the Y register. So that's like a page Y direct and a page Y indirect mode that we can choose. Yes, right. So for these we have the X and, no, let's get back. This is the, these are the addresses for the RAM chip, the X and Y. And let's have a look at the branch addressing. So if we look at the EEPROM with the program in it, so behind this is are the operands. And in a branch, if you want to jump to somewhere else, you can use those addressing modes, but those are always within, now in a branch, you can only jump within the page that you are already in, and only with absolute numbers. So you cannot say, I want to jump 5 instructions further. You can only say, I want to jump to position 25, because that's from the operand. You only have the operand to tell where to go to. So that's a bit of a problem, but we can fix that in software. So if you make a software compiler or something else that calculates the exact number to put in, that'll work. But it will be a little bit of a problem if you want to jump to a different page. So how do we do this? Well, you could do this in software by jumping to the end of the page, and then the next instruction will be in the next page, and then you build some software there. But we really wanted to have some better solution to jump anywhere in the memory. So we needed a far jump. And remember that for the 8 conditions we had for the branch instruction, there was one that never was true. So that's a bit of a useless instruction, an instruction that never jumps. So let's rewire that in hardware to actually do jump, but do a far jump. So we rewire this instruction to a far jump, and we use the Y register as the high bits, kind of the page that we are jumping in. So we have the operand and the Y register for far jump. So that was also quite easy to do. All right, so next we need the buttons and the LED matrix. Input and output is not that complicated. For output, we have the option to put the result of the ALU into the output buffer, to the output, using addressing mode. And to input, we can copy the input to the bus, and from there we can store it in memory or in a register. So as you can see, we have for output, we have the addressing mode, where these 2 cases where the output of the ALU goes to the output. So this is the way to do output. And for input, we have the bus access 11, which says the input goes to the bus, and we can, with these bits, decide where the bus is going to. So we can put the input into the accumulator, or the input to X or Y, or directly to the output. Now, the LEDs, that was the first plan, but there was some point of time where somebody on Hackaday built an Arduino that could do VGA. And we thought, so VGA is probably not as difficult as you might think. And if you look at VGA, if you look at 640 by 480 EGA, then it's quite simple. You need to output bits with color information, and for each line there is an H-sync signal. And if you are at the bottom of the screen, you need to send V-sync signals so the monitor can sync. Since we're using a RISC architecture, we exactly know that each instruction takes one clock cycle, so we know the timing of each clock cycle. So it's fairly simple to get the timing right to make a valid VGA signal. This is actually the reason that the board is running on a 6.25 megahertz clock. So we had a bit of we could play a little bit with the clock speed to make it faster or slower, but this was the clock speed we chose to make the VGA signal generation doable. This is also the reason that the X register is a counter and the Y register is not. So this is to make it really fast to go over a whole lot of addresses, so we can bit bang the information in the memory directly to VGA out without using too many instructions. So here we see some V-sync and H-sync signals on the oscilloscope. If you look at the screen, normally not the whole screen is shown on your monitor, only a part of it is shown, and the axis part is where the sync pulses take place, and on the lines that you also don't see, the vertical sync pulse is taking place. In our case, a problem now is that during this time, the red box, we are constantly outputting bits to the monitor, and there's no time left to do anything else in our computer. So this is just bit banging stuff out of VGA. And we only have the green part left to do some actual work. So this really slows down the system quite a lot. And also timing is critical. So if you make a program, you can only run the programming bits in this space, and we need to stop doing useful stuff and start doing VGA again when the next screen is up. This is also quite difficult, all the timing, and this can also be solved in software. So the software takes care that all the timing is correct. Now, because of the speed of the RAM, we have another problem. It's not feasible to get enough bits, the 640 bits per line, onto the screen. So we only do a quarter of that, 160 pixels. For the vertical, we also have the problem that we don't have enough memory in EEPROM to store complete pictures. So we also only show 1/4 of the lines. So each line we output 4 times. So you see 4 times the same line, and on each line, each pixel is 4 pixels wide, so you get blocks of 4 by 4 pixels in effect. What we also can do is we have a retro mode, which looks really 80s, where we show the same line 3 times, and then the fourth time we leave it blank. So you get all these tiny black lines, which has as an advantage that we can use those lines to do some actual calculations. So this will speed up the system. But VGA is now really, really simple. This is just a couple of resistors to the VGA plug. That is it. And we have 2 bits per color, per RGB. So in total we have 64 colors that we can produce, and this was actually one of the first test pictures that was produced. So that's a resolution. So this is all that we have. We have an output register to store the value, the resistors, and there's the VGA connector. Now we built this on a breadboard. Then we built the PCB. That was actually quite hard. That probably took most of the time of the whole project to build an actual PCB. We had a prototype that had a few errors. spot the error on this board. We had a plug the wrong way around on the board. But it was nice. We only needed to change 2 things, and the plug was the wrong way around. And other than that, this is the actual board. It ran the first time, so we're really happy with that. So let's get back to the RAM memory. So we have this X++ possibility, addressing mode. So that is especially to read from the RAM and bit bang all that information onto the VGA port. So by using this instruction, the X register is automatically increased, and we don't need any extra instructions to do so. And it's also nice because we don't wrap to the next page. If you are at the end of the page, it just starts again at 0. So if you keep on reading, you keep reading the same line. Now actually the top part is not there because the RAM is only 32K. So that's actually replicated, and also the VGA lines are only 160. So the first 160 bytes we use to store a VGI line. And if you get to the end, you wrap around to the beginning. And so the page 0 is a bit special because you have special addressing modes to get to that page fast. And this is replicated in the upper 32K. Right, so we have a system that's now doing VGA output, but of course we want more. Can we do more? It's really hard to add more output without adding a whole lot of more hardware. Or is it? Well, we thought, you know, we're doing VGA and we have this sync signal, and during the sync signal, there is no VGA output that we need. There's nothing put on the screen. So if we use the 8 bits that are there for something else during the H sync, we have for each scan line, we have the possibility of outputting another 8 bits to something during the sync. So we did. So during the sync, we have 8 bits that we use. 4 bits we use for blinking lights, because you need to have blinking lights, and 4 bits we use to do audio. So we have a 4-bit DAC, a digital audio converter, and 4 bits of blinking lights. So here's so we need 1 chip for extended output, blinking lights, and audio. Really, really simple. Well, to play games you also need input. So how do we do input? And we thought about this, and we decided to buy something common off the shelf. We looked around on Chinese marketplaces, and we found the Famicom controller, which was, I'm still not sure if this was a knockoff of the NES or the original NES.
Official Japanese NES.
It's the official Japanese NES. And what's really nice about this controller is that, in contrary to the original NES controller, the Famicom controller uses a really cheap DB9 serial plug. So that's what we ordered. Then we found out that it contains some electronics inside. It's not just one line per button, but you need to send to the controller a signal that it needs to start bit shoveling out the values of the buttons. And then you need to send signals indicating that you want to read a bit. How do we do it? Well, we have each screen, we have a VSync signal. If we piggyback the VSync signal to the Famicom controller, we can send the signal. You need to start bit shoveling out the information of the buttons. So each screen, it gets a signal to send the data. And now we need to bit shovel in the data, so we use the H-sync. So every screen line, the controller gets a signal, you need to give me 1 bit. And after eight syncs, 8 lines, we have a full byte containing the information of the controller, the buttons on the controller. So we can solve this with a tiny amount of hardware, and all we need is some software to do the rest for us. So the software needs to make sure that between the line number 8 and the last line, we read the value of the controller. So that's all that we need for the input controller. So what have we got? We have a CPU, but we don't have a microprocessor. The CPU is built out of common TTL logic. It's a RISC architecture. It runs at 6.25 megahertz for the VGA. We have 32K of RAM. If you like, by the way, you can upgrade to 64, but you need to solder in 2 extra wires for the addressing. We have VGA output, we have sound output, we have blinking lights, we have controller, and we have built an interpreter. So let me get to the software that I was talking about that needs to solve all kind of problems in the hardware. We could have gone with you could go with approach 1, which is you write assembly and you burn it onto the EEPROM and you run it. You could do this, you could compile software written in a higher language. Maybe you write something in C and you compile it into assembly and then you burn that on an EEPROM. Or there's something in the middle, which is you have some kind of interpreter burned in the EEPROM. You also burn something in a somewhat higher language in the EEPROM. And when the system boots, the interpreter will run that code, interpret that code, and then run it. Well, approach 1. No, that's way too difficult with all the timing constraints and all the other stuff. And we actually chose for approach 3. Could have also gone for 2. But we chose for 3, which means that in the EEPROM, during boot, an interpreter will start and will read code in a somewhat higher language and start executing that. And what is a somewhat higher high level language? That's the GCL, the Gigatron control language. Some people do know GCL. So here you see GCL code. It is not machine code, but it's not really high level, but it'll do for simple programming. So again, this is what it would look like in BASIC. This is the actual interpreter code. It looks a bit like the language false. And this also inspired, for instance, brainfuck as a language. So we use 160 bytes in each RAM page to store the image that goes onto the screen. I showed you this before. So we have the 0 page below. Let's zoom a little bit in on the lower part. So this is the actual RAM, 32K. And if you look at the bottom rows, with the interpreter, we use the bottom part of the RAM for all kinds of housekeeping stuff. We have some system program variables here. We have a virtual CPU stack with a virtual stack pointer. Remember, there is no real stack pointer in the hardware, but the interpreter has a virtual stack pointer. There's a video frame indirection table. I'll explain that later. And here we can put some virtual CPU code. There's also some stuff that's needed for audio, shift table. And the main part of the memory is to hold one screen to output on VGA. So there's 160 pixels per line, so we have a few bytes spare that we can use to put in extra code or data or whatever. Now the video frame indirection table, what that does is it points to the beginning of each video line. So if it points to here, then this video line starts here and it goes up to there. And the advantage is that it now becomes really easy to do horizontal scrolling. Just change the indirection table and your screen starts scrolling. That's nice. So the interpreter emulates a virtual PC that's not really in hardware. It runs instructions that are in a somewhat high-level language, vCPU instructions, using a virtual program counter. So it actually emulates a 16-bit architecture with a 16-bit accumulator and stack pointer. And what it also does for the timing is keep track of all the amount of clock cycles that each instruction takes. So it looks at the next virtual instruction. It needs to turn that into machine code, but at first it checks if there's enough time left to do that before the next video line needs to be output. So it takes care of all the timing. And it's a bit like Sweet 16. There was a program on Apple, built by Steve Wozniak, who also needed a 16-bit architecture on an 8-bit machine. So the fun thing is that we have an 8-bit CPU with a Harvard architecture that I've been explaining how it works. But in effect, with all the software that we added, we end up with a virtual 16-bit CPU with the Van Neumann architecture. And that's all thanks to the software. What can it do? It can do this. This was one of the first programs that we made for it. And what's fun is that it's a nice small board. This is a Commodore 64. Anybody's, well, it says here what it is. It's a Hercules card, video card. So that video card alone is a bit bigger and more populated than the Gigatron. So it's interesting, there's a lot of hobby projects building interesting hardware, but some need a microprocessor, like Commodore 64, which we didn't want to do. Some need multiple boards, which is also nice. This is a really nice project, the My CPU. Or they are single board without a microprocessor, but they have really limited input-output. They're still very nice tools, but we wanted to integrate that all. So that's what our board does. And we're currently busy in making it into a kit. So we are now still waiting for these wooden boxes to be made. And when they are here in hopefully a couple of weeks, they will be ready. So this is the PCB. So we plan to make kits of this. So you get the PCB, you get a bunch of TTL chips, you get a manual with actually it's 48 page telling you how to do soldering, how all the electronic components work, contains full hardware schematics, and that should be enough to build it. You get some bag of components. So this is the whole kit. And if you'd like to know more before I start demoing, there's a mailing list if you are interested. Source code is online, is open for you to see. There's a guy who wrote a visualizer, which is really great. It's kind of an emulator to run Gigatron software on your own PC. And there's over 1 hour of videos describing how to build the system. What's also nice is that just 2 hours ago, the ROM was finalized. So we now have the ROM that we will be shipping with, hopefully. And without further ado, let's see if I can get a system to run.
Oh yeah.
Oh, there's some part. Thank you. Some part is missing, but it should work. The fun thing is that we have a 32K of usable ROM, but it's already full. So this is this is all that fits in there. So we have a few games like Snake. You can see the retro mode with the. It's quite hard. I can turn it off. So this is the normal mode. For this game it doesn't really matter in the speed, but for other games you can see a notable difference. Reset.
Zo, even om.
Okay.
Dat niet zo. Dat is geen voorrecht, dat is het.
And we have a oh, it's you can't really see much of it. Oh yeah. Yeah. Oh, I have the ROM that was just finished also includes a clock here. It's not here. Yeah, and what's also interesting is that one of the problems is that we have EPROMs. So if you want to put other code in there, you can, but you need to have an EPROM eraser and EPROM programmer. They're not that expensive, but probably not everybody has one. So we thought of a way to put in programs later on. And we built a loader. The loader is actually working. You can connect to the controller port an Arduino to upload code into the RAM. So this interpreter will also input actual high-level code and start running it. So that's also nice for future upgradability. Okay, maybe we have 1 minute left for questions.
How long did it take you to build all this?
Building was not so hard actually. That took maybe a month. But making the PCB, that was maybe 3 months. That was the biggest job.
But all this in 4 months? It's
Yeah, well, actually, with everything, as I said, we started in December 2016. I joined in June. We tried to spend about 1 or 2 days a week. So you can calculate. Yeah, it's quite a lot of time.
Other questions to Walter?
yes. How much about cost? Roughly?
There you go.
The idea is that it will. The price will be 160. $200, but we will do the first batch goes out for €150, excluding shipment. Also, I have to thank the people from the batch project, because we took some hints from them, and we also didn't score any parts from China, where we had a possibility that they were maybe not quite to spec. So it should all work. The only thing that we bought in China are the controllers and the USB cables, and actually USB cables are already quite bad according to their specs, but they're usable.
Other questions to Walter about this awesome project? No? Okay, then I would like to thank Walter for his amazing talk about this nice piece of hardware.
All right, thank you.
And give it up for Walter.